Hey guys, this is the first video of chapter 9. Our chapter topic is differentiation, and in today's video we're going to look at the introduction to differentiation, having a look at average rate of change and also instantaneous rate of change. So let's start with the average rate of change. So our average rate of change, or AROC for short, is the gradient of the line connecting 2 points on a curve. So it is the gradient of a line connecting 2 points on a curve. So for example, if I drew a quick curve, let's say this is f of x equals x squared. This is y, this is x. Let's just pick two random points. Let's say this is point A, which means our y value is f of A, and the point up here is B, f of B. Then when we talk about the average rate of change, what we're doing is we're drawing a straight line from our 2 points, so from A to B, like that. And we're going to find the gradient of this line. M is equal to the average rate of change. So in order to find the average rate of change, we want to find the gradient, and that's just through using our gradient formula, y1 minus y2 over x1 minus x2. So we have f of b minus f of a, all divided by b minus a. So this is how we find our average rate of change. Now the average rate of change gives us the gradient of a line connecting two different points on a graph. But what if we want to find the gradient of the graph at one particular point? So if we have a look at this parabola, we can see that the gradient of the graph changes depending on the x value, because the parabola is constantly changing in shape. So using differentiation, we can find the gradient at any one point on the graph without having to find the average between two different values. So the way we can do this is we follow the same structure as we did with looking at our average rate of change. So if we draw another set of axes, and let's just use the same graph again. So let's just use our parabola again. Like that. This is f of x equals x squared, y, x. Let's say we want to find out what the gradient of the graph is at this point over here. And let's just label that a, f of a. So we want to know what the gradient is at this point. So the gradient at this point we can kind of draw. If we draw a tangent to the graph, and a tangent is a line that just touches the graph, so like this, touches the graph just once, this tangent will intersect with the graph at our point A, f of A, and the gradient of this tangent is the same as the gradient of our graph at point x equals A. So we want to find what the gradient of this tangent is going to be. And one way of doing that is by using our average rate of change formula like this. So let's say we pick a point on the graph again, like so. This one's b, f of b. We know that if we draw a line connecting these 2 points, we can find the gradient of that line. But the gradient of this line is not going to be a good estimate of this gradient itself. However, if we bring b here closer and closer and closer and closer to a, and if we bring b as close as we can to a and then find the average rate of change between those 2 points, so say it was here, then the gradient we find here will be a much better estimate of our gradient at the particular point A compared to if B was further away. So what we want to do is we want to find the average rate of change between 2 points, but the 2 points have to be really, really close together. So let's label this point A plus H. So H is just the distance between A and this point, and this is f of A plus H. We can say that the instantaneous rate of change, or the IROC, is equal to f of A plus H minus f of A, or divided by A plus H minus A. And it's going to be more and more accurate when our distance h gets closer and closer and closer to 0. And the way we can notate that is through what we call the limit notation. So we can show that we want h to be as close to 0 as possible by saying our instant rate of change is the limit as h approaches 0 of this entire equation. So what this limit notation means is that we want to find what the value of this gradient or this equation is going to be as h gets closer and closer to 0, or as it tends towards 0. As h approaches 0. Because when h is equal to 0, there is no difference between these 2 points, meaning that our average rate of change between the 2 points is going to be the gradient at our point x equals a. So let's use our function f of x equals x squared as an example for finding the instantaneous rate of change at point A. So if f of x equals x squared, then the instantaneous rate of change at x equals a is equal to this entire function over here. So we have the limit as h approaches 0 of f of a plus h, which is a plus h squared, minus f of a, which is a squared, all divided by a plus h minus a, like that. And then we can simplify the numerator. So this is the limit as h approaches 0. A plus h squared minus a squared gives us a squared plus 2ah plus h squared minus a squared. Everything divided by h. And then this simplifies to limit as h approaches 0. A squared minus a squared gives us 0. And then we can cancel out h's as a common factor, giving us 2a plus h. And how we solve these limit equations is we just substitute what our h is meant to be approaching. So if h is approaching 0, we substitute h equals 0, and that gives us 2a. So the instantaneous rate of change at x equals a for this function here is equal to 2a. In other words, the gradient at this point, I'll write that here, the gradient at x equals a is 2a. So no matter what value a is along the graph, we just substitute that x value into here, and that's going to give us the value of the gradient of our graph. And this leads straight on to our derived function. So if we look back at f of x equals x squared, we know that the instantaneous rate of change at x equals a is equal to 2a. But because we never defined a value for a, we know that we can substitute any x value along this graph, and the gradient of the graph at that point is just going to be 2 multiplied by whatever the x value is. So in a sense, we've found a function that will give us the gradient of the graph at any particular point. And this is what we call our gradient function. So the gradient function, or the derived function, so our gradient or derived function is a function that gives the value of the gradient of a particular graph at any point x. So in this case here, our original function is f of x equals x squared, and we know that the gradient function, which we use f dash of x to denote, is equal to 2x, because we've found the instantaneous rate of change for any type of x value. Once we substitute the x value in, we get the value of the gradient for our function. So looking back up here, if we pick a point, let's pick this point 1, 1, we know that the gradient of the graph at this point is going to be 2 multiplied by 1. The gradient of the graph at x equals 1 is going to be 2. And we can do that along the entire length of the graph. So that's our derived function. We can use f dash of x to notate that. We can also use dy over dx. So these two mean the same thing. And we use dy equals dx when we start off with a function y equals f of x. So y is being used to define our function, and then dy dx is what we call the gradient function. We use f dash of x when we're given f of x equals blah, 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 and then our derived function is f dash of x. Now, we've already touched on how to find the derivative function through this formula over here. And this is what we call differentiation by first principles. So differentiation by first principles basically just states that our gradient function f dash of x is equal to what we've done here. So we pick 2 points that are really close together, separated by the distance h, and we see what happens as h gets closer and closer and closer to 0. So our gradient function f dash of x can be found by the limit as h approaches 0 of f of x plus h minus f of x divided by x plus h minus x, which is just the h. So we want to find the average rate of change between 2 points, but the 2 points are getting so close together that the distance between them is approaching 0. So this is how we use differentiation by first principles to find what the gradient function actually is. So let's work through an example. So we're given f of x, and we want to find the gradient function using differentiation by first principles. So that gives us f dash of x equals the limit as h approaches 0 of f of x plus h, which is x plus h squared plus 2 multiplied by x plus h, minus f of x, so minus x squared plus 2x, or divided by h. So now it just comes down to simplifying this function, or this equation. So f dash of x is equal to the limit as h approaches 0. Make sure you do write this limit in every single line of working out. Let's expand x plus h squared. So that gives us x squared plus 2xh plus h squared plus, we expand this out, gives us 2x plus 2h minus x squared minus 2x. So I've expanded this bracket out as well. And the entire thing is divided by h. And then we collect all our like terms. So our x squared and negative x squared cancel out. 2xh stays there. H squared stays there. 2x minus 2x gives us 0. And positive 2h stays there. So in our next line, we have f dash of x equals the limit as h approaches 0 of 2xh plus h squared plus 2h all over h. And then all of these terms have a common factor of h, so we can cancel that out. So then we have the limit as h approaches 0 of 2x plus h plus 2. And then when we finally simplify our fraction, we can then address the limit. So the way we eliminate this limit is by substituting h equals 0. So we just substitute the number that h is approaching. So by substituting h equals 0 into here, we get f dash of x equals 2x plus 2. So this is our gradient function, meaning that when we substitute any x value into here, we're going to find the gradient of our graph f of x equals x squared plus 2x at that x coordinate.